Okay, today we are going to calculate the internal energy in a system and determine the effects of pressure and volume on work. We're also going to review Hess's Law and apply it to calculating the enthalpy change in a process, given that that enthalpy changes in other processes and could be combined to the yield of the reaction of interest. So there is a pretty extensive derivation that we're going to go through with energy and work. It is worth it because it shows how delta H is related to delta E. Just be aware, 19b, thermodynamics first law, that is the quest that pairs with this play posit. Okay. So energy and work. So on the last play posit, I gave you that equation briefly for energy. We have our heat, which is Q, plus our work. And we also have to take into account pressure, because some of the other examples we looked at were not under constant pressure, or were under constant pressure. Some of the examples we're going to look at now are not under constant pressure. So pressure is our force divided by our area. And we can rearrange that, right? We can rearrange that to get force on one side, and we end up getting force is equal to the pressure times the area. Well, if we think about that value, we know that that is related to work. We can incorporate our pressure into our work by saying the force times the distance is equal to the work. And since we have our force value here, we can take our pressure times our area and we can plug it in there. So we end up getting that force is equal to the pressure times the area and then times the height, right? Area times height, what does that give you? Well, it gives you a volume. One of the things we want to keep track of is that if we're looking at things with work where it's done by the system, it is a negative sign that we have to put in front of there. But area times delta H does give you your volume, and that is where the P times delta V comes from. So work is actually equal to P times delta V. Now, work done by the system is what we will typically see, typically because we want to look at situations where things are expanding. If things are being compressed, work is being done on the system. So we could substitute delta H into that equation, and we end up getting delta E is equal to delta H minus P times delta V. All right. Now, we can also rearrange that to say delta H is equal to delta E plus P times V, delta V, right? And if we have pressure and volume, this is where it's going to get really weird because we'll see problems like this later on. Pressure and volume. When we're thinking pressure and volume, we can think of gases. We know PV equals nRT, right? So if we've got PV and it's equal to nRT, look how evil that is. Man, what a time. So you can actually use the energy of your system, the energy change in your system, with the moles, your R value, and your temperature to get your delta H. That's a little wild. That's crazy. Man, okay. Now, something I should have said, if we're looking at our delta V, so delta V can be positive or negative as well. In this situation, we made it negative because work is being done by the system. We assumed that work was negative, but what makes it negative, actually, if we look at our derivation, VF minus V initial, if you have a larger initial volume, you will become a negative number, whereas here, if you've got a smaller initial volume, so this is small, this is big, and this will be a positive delta V. So think about that. If your final volume is small, you get a negative delta V times this value gives us a positive work, right? Because we know it's negative P delta V is equal to our work. So if we've got a negative delta V in here times a negative P, we get a positive W. So this is another way we can just show that when we are compressing a system, if our volume is going from big to small, then the numbers will work out, and this is where the positive and negative W comes from. If we have a smaller volume to start and we go to a bigger volume, we are expanding our system. It's going to be a positive delta V. It's a positive delta V. Negative times a positive gives you a negative, and that will affect our original equation up here. Okay, cool. So the problems dealing with energy and PV work are actually fairly easy. You just have to pay attention to the wording. So delta E for a system undergoing an endothermic process in which 15.6 kilojoules of heat flows and where 1.4 kilojoules of work is done on the system. All right, so done on the system, that's a big clue that this is a positive W. This is a positive W, sorry. Positive W. All right. And we are also told it's endothermic. So if it's endothermic, what does that mean for my Q? Q is also positive. So if my delta E is equal to Q plus W, and I know these are both positive, we got 15.6 kilojoules plus 1.4 kilojoules. I don't even need a calculator for that. I can figure out really easily that is 17 kilojoules. So 17 kilojoules of energy is our change in energy in this process. Fairly simple. All right, PV work. So remember that your work is equal to negative P delta V. That's the derivation we came up with before. And that delta V is our V final minus V initial. Our initial volume is 46. The final volume is 64. This is easy. 15 atmospheres, 15 atm. Right, negative 15 atm times 64 liters minus 46 liters. And we end up getting, what was that, negative 15 atmospheres times 18 liters? 18 liters? Yeah. And when we multiply those, we end up getting 270 liters times atmospheres if we're looking at our units. 270 liter atmospheres. 270. Okay. That is the amount of work being done on our system. Pressure and volume work. Okay. All right. So some other types of problems you'll see where we're looking at delta H at constant pressure. Here we've got 1 mole of methane. It's burned at constant pressure, and 890 kilojoules per mole of energy is released as heat. This is huge. If we're releasing energy, what does that mean about my delta H? What should my sign be? It's exothermic, so my sign should be negative when I'm all said and done, okay? It's really saying we've got a negative 890 kilojoules per mole being released. And we want to calculate the delta H for a process that's only 5.8 grams of methane. Well, this key here is our units. This is just a units game. We've got this many kilojoules per mole, per 1 mole, right? 1 mole of methane here. And so if we had less than that, we can start with our grams of CH4 methane. If we have grams of CH4, what should we convert it to? Should have said moles, all right. So molar mass of CH4 is needed. 1 mole on top because that's where we're going. We want to cancel our molar mass, so we end up dividing by it. That's why it's on the bottom of our fraction. So we got 12.01 plus 4.04. We end up getting 16.05 grams as our molar mass. And let's check our calculator. Let's see. 5.8 times 1 divided by 16.05. All right, we get 0.361. 0.361 moles of methane. And we know how many kilojoules we have per mole, and we've got less than 1 mole. We can use that as a conversion factor. What goes on the bottom? 1 mole. What goes on the top? Negative 890 kilojoules. All right. We can go through, do our math. We end up multiplying by our negative 890 divided by 1. Oops. Negative 890 divided by 1, right? That's our fraction. 890 is on top. And we get negative 321.6 kilojoules. All right, negative 321.6. And I guess with kilojoules, we can go with 2 sig figs here. The negative 320 kilojoules of energy. And this is our delta H. Not too bad. Okay. Hess's Law. This is my favorite. I love Hess's Law. In honors, we got a brief glimpse of this, but honestly, I think we're pretty solid with Hess's Law already. We've been doing an application of it in our electrochem balancing of reactions. A couple of key things we need to know. When you have an element in the standard state, it will have a delta H equal to 0. So 0 in the standard state. So we got to think about what a standard state is. Remember that your standard state. And we go with lab conditions here because no one wants to be at 0K, or not 0K, 273K. We don't want to be working in a lab that is essentially frozen. So we use 25 degrees Celsius. That's 298K. 298K, 1 atmosphere pressure, because that's what we're normally acclimated to, and 1 molar. So those are our main conditions. So in a standard state, it is 0. So if you saw something like a diatomic gas, like O2, the delta H value that you would see would be 0, because we know O2 is a diatomic and it exists naturally as a gas. That's its standard state. Okay. So we're getting into the second method here. I think it was the second method, Hess's Law, and then we also have enthalpy of formation. They are related to each other. There's a way we can calculate enthalpy of formation another way, but Hess's Law is just the first way we can do this. So we can end up writing the formation of 1 mole of a compound from its elements in the standard state. This is your definition of enthalpy of formation. Enthalpy of formation. And your enthalpy of formation, we use the symbol delta H, but it's at a standard state, so we use that, and we have F. So the F just is formation. And this just means it's standard state. Or if you wanted to, you can just say naught. All right, delta H naught with an F. Now, when we look at the rules for Hess's Law, we are going to treat those rules pretty similarly to the way we did with electrochem. If you reverse a reaction in Hess's Law, you still reverse the sign of delta H. That's easy. We've got that down. Now, this is the new rule. This is different from electrochem. That cell potential, your E naught, was not impacted by the coefficients, and when you multiplied your reaction by those factors to balance your electrons. But with delta H, it is actually affected by that because it is proportional to your moles, right? We typically report delta H in kilojoules per mole, and since we are reporting it in kilojoules per mole of our reaction, everything's proportional to your coefficients, because that's your mole ratio, right? So if you multiply a reaction by a factor, you also have to multiply delta H by that factor. If you divide by a factor, you have to divide delta H by that factor. Okay, so with adding reactions in Hess's Law, we have our rules, but let's make sure we know how to add even just the reactions properly. You could have a reaction, let's say A goes to B, and even B goes to C. All right, if we were to add these together, you would see that you'd have A plus B and B plus C. Well, we have the same thing on both sides. We can get rid of that B and simplify it to just A goes to C. Now you could also have a situation where those numbers are uneven, and that's okay. You could do the same thing where you could have, say, A goes to 2B and B goes to C. I could have A plus B goes to 2B plus C. Well, I see I've got one B on this side, that can cancel out. I only have two B's on this side, so one of them will cancel out, but the other will remain. So it will turn into 1B on this side. Right? Now you could also do something else where you've got things on the same side, so C goes to 2B, and you could have A plus C equals 4B, and add things up that way too. Just keep track of your coefficients because that will be huge for figuring out where things will cancel out, okay? You can even have a half of our reactant, so let's say if we had like on this side, well, I like this one. So if we got A gives us 2B and we've got 1/2 B gives us C, we could get A plus the 1/2 B would cancel, and we'd actually lose a half from here. So we could just get A gives us 3/2 of B, right? Because we took away a half. 2 is the same as 4 over 2 plus C. So you can cancel out halves of a reaction too. Just be careful with that because in the end, you want to have the right balance equation as your final step. Okay. Okay. So here's our first example. All right, I believe this is boric acid. So we got some boric acid and some interesting complex here. And we want to know delta H for this reaction. Okay. So first things first, I want to make sure that the things that I want on the reaction side are in the right positions up here, right? So I see B2O3 as a product, that's good. I see water as a product, that's good. But an issue I'm seeing is that here I've got some water as a reactant. I also see species in here that I don't want, like HBO2, and they're on the same sides of the equation as well. So for the things that are already in the right spot, I probably don't want to reverse them, but I do see that this reaction here is on the wrong side, so let's reverse it. Let's see where that goes. We get 4HBO2, and that gives us this plus our water. Now, if we reversed our delta H reaction, what happens to our value? Becomes positive 11.3. Good, 11.3 kilojoules per mole. And I like to cross it out once I've manipulated it, just so I keep track. Okay. Now, if I was to add all these things together, it does not look like they would cancel in the current form. So if I wanted my HBO2 to cancel out, I would likely need to multiply this reaction by 4. So let's multiply this by 4. I get 4H3BO3 and 4HBO2 and 4 waters. And what happens to my delta H? I have to multiply this by 4 too. All right, so we get negative 0.08 kilojoules per mole. And now we just have to check and see if everything else will cancel. Well, I see that this will cancel here. That's good. I now have 4 of these that will cancel here, and that's good. And the rest is water, which I want. So let's bring this all together. We've got H2B407, we got 2B2O3, and water. So these are my 3 reactions. 17.5 kilojoules per mole. Okay, so let's add these all together. And I'm going to use different colors. I see 4 HBO2 on this side and 4 on this side. They're on opposite sides, they will cancel. I see 1 on this side, 1 on this side, they will cancel. And in total, I get 4 H3BO3. I see 2 B2O3s. And I get a total of 6 waters. Oh, well, we're on the right track. We have all the products that we want. The issue is our coefficients are off. Well, look at these numbers here. Remember, this is a 1. This 2, 1, and 3 ratio is a multiple of 4, 2, and 6. We could end up adding our numbers together. So let's add them together. 11.3 plus 17.5, and then plus a negative 0.08 gives us 28.72 kilojoules per mole. And that's your delta H for this reaction. But we want something that is half of that. So let's halve everything. You can multiply by 1/2. We get 2H3BO3. We get 1 BO2 or B2O3, and we get our 3 waters. This is what we wanted, right? Now, if we do it to the reactant side, or not to the reactant side, to the reaction, we have to do it to our delta H. So we end up dividing that by 2. We get 14.4 kilojoules per mole if we stick with our 3 sig figs. And this is the delta H of reaction here. So evaluate it. What does this delta H mean? Is this going to be an exothermic or an endothermic reaction? Should have said endothermic. Good.